Hey guys, welcome to Lesson 5, the characteristics of rational functions and their graphs. This is topics that we have gone over in Algebra 2, so some of it should be a review for you. Just quick little definitions. The domain of your function, it is all of your x values. So if you think about a rational function with a vertical asymptote at some particular x value, a horizontal asymptote, or it could be a slant asymptote. I'm just doing a horizontal one. And then maybe we actually have like a hole in the graph as well at some other x value. So our domain is going to be all of the x values except for the vertical asymptote and except for the value, the x value of where the hole is. Okay, the range is going to be from bottom to top, so that'll be all the y values except for the value at your horizontal asymptote and the y value of the hole. And then we're also going to talk about how do we get those vertical and horizontal asymptotes and x and y intercepts. So real quick, for the vertical asymptote, you are going to be looking at the factors in the denominator that don't reduce. Okay, piece of cake. For the horizontal and the slant asymptotes, you want to look at your function before you factor it and determine the degree of the function. So if you have the numerator being less than the denominator, so that would be y equals an x over an x squared, that's going to give you a horizontal asymptote at 0. If you have the degree greater in the numerator, then that's going to give you a slant asymptote, which you actually will need to do long or synthetic division in order to get the equation in slope-intercept form, y equals mx plus b. Okay, and then our last one that we're going to look at is if the degree of the numerator and denominator are equal, so if they're equal to each other, so if I have a y equals 2x squared over a 5x squared, then you're going to take the coefficients of those terms, the x squared terms, and your horizontal asymptote in this example would be 2 over 5. Okay. Our next little chunks are the actual holes. So holes occur when you have factors that reduce. And what that will do is it'll give you the x value, and then you'll substitute that x value in to determine the y value. You always want to get an ordered pair so you can actually plot that hole in the graph. Your x-intercepts come from the numerator factors that don't reduce, and your y-intercept, that just means you let x equal 0 and solve for the y. So I personally like to do those first. I'm going to kind of do things in the order in which I like to do them. It truly doesn't matter, whatever way works for you, as long as you get it going. So here we go. First example. F of x equals 3x over x squared plus x minus 2. So the first thing that I want to personally look at is the y-intercept, and that's because I can just substitute a 0 for the x's, and what's going to happen is I'll just get 0 over negative 2, which is 0. Okay, so my y-intercept is the ordered pair 0, 0. Now, if you remember, that's actually going to be the exact same thing as your x-intercept, because it's the origin. That doesn't always happen. That was just a little side note that we had there. Okay, so the next thing, again, before I've done any factoring, is I want to look at the horizontal and slant asymptotes. Okay, so again, check the degree of the function. We've got a 3x over an x squared. So this one has a larger denominator degree, so it has a big bottom. So the horizontal asymptote is always y equals 0. Okay, remember, if they were the same, we would divide the coefficients in front of the terms. If it was top heavy, it would be a slant. You're only going to have one or the other. So this one has a horizontal asymptote at y equaling 0. So we're going to say none for the slant asymptote. Okay, so I've taken care of everything I can do before factoring. Now I want to go ahead and factor to check to see, are there any terms that can reduce to give me a whole, and then proceed on with vertical asymptotes, domain, and x-intercept. The denominator of our function, x squared plus x minus 2, has factors of x plus 2 and x minus 1. There is nothing to reduce between numerator and denominator, so we do not have a whole. There we go. The next I want to check is vertical asymptotes. So any factors left in the denominator, when you set those equal to 0, will give you your vertical asymptotes. This function has a vertical asymptote at x equaling -2 and a second one at x equaling +1. Those two vertical asymptotes, along with a whole, if I have it, are the values that break up the domain. So we're always going to start at -infinity on the left, travel to the first value, either a whole or x or vertical asymptote, whichever you come to first. So -infinity to -2, union. Now I got to go between these two asymptotes, -2 to 1, and then union 1 out to +infinity. So we're always going to start at -infinity on the left, traveling to +infinity on the right, and split it up with vertical asymptote and the x coordinates of the whole, if you have them. Okay, and then our last thing that we can get from our function, look at the numerator, set it equal to 0, and it will give you an x-intercept. And again, this case, our x-intercept is 0, 0, and that was the same as our y-intercept. Okay, I personally like to get the range after I've looked at the graph just to double check. I'll show you how we can get that, and also our end behavior. So our end behavior statement is, as x approaches -infinity, f of x approaches, or the y values approach what value? And then as x approaches +infinity to the right, what do the y values approach? Positive or -infinity or some y value. Okay, so for the end behavior, if you have a horizontal asymptote, then your end behavior is going to go to that particular value. End behavior for functions that have a slant asymptote is going to approach +infinity on one side and -infinity on the other, depending on the slope of the slant asymptote. Okay, and we'll get to one of those that I can show you in a graph. So in this case, our example, we have a horizontal asymptote at y equaling 0. So when we sketch the graph, the function is going to approach 0 to the left and 0 on the right-hand side. Okay. Our last little piece that we can do is the range, and this is going to break up all of the y values that are not included. So the only y value not included is where the horizontal asymptote is at 0. So we're going to say -infinity to 0, union 0 to +infinity. These are just the characteristics of this function. I'm going to briefly show you a quick rough sketch of what the graph would look like, just so you can kind of make connections, and then we'll scooch on with characteristics of the remaining examples. So I have a vertical asymptote at x equaling -2, a vertical asymptote at x equaling +1, and both my x and y intercepts are at the origin. I also have the horizontal asymptote at y equaling 0. Okay, so in this example, we have a section between two vertical asymptotes. We call that vagus. Anything can happen. You can cross asymptotes and do whatever you need or want in that particular section. Since we don't have any other points to help us sketch, what we would do is we would look in the calculator to help us get some points. So I need a point to the left of -2, the other point at -1 between the two vertical asymptotes, and another point to the right of x equaling 1, so I'll pick +2. That's going to give you values so that you know, are we sketching above or below that horizontal asymptote. When x is -3, I'll get a -9 over 9 minus 5, which is 4, so -9/4. So I'm going to go to -3 and then down a little bit past the 2. Okay. Should you have more points? Yes, you should. But rough sketch, I have a point. It is below the horizontal asymptote, so to the right, I'm going to fall down and approach the vertical asymptote on the right. I will increase and go up to the left, approaching the horizontal asymptote. Okay, now what happens in between the vertical asymptotes? When x is -1, that would give me a -3 over 1 minus 1 is 0 minus 2. So a -3 over -2 is +3/2. So that means I'm going to be up above. Okay, so I have this point where I am above. I have that point above the asymptote. I have the point at the asymptote, so then I'll decrease on that other side. Alrighty, so this side goes up, pass through the intercept, and approach the vertical asymptote the other direction. All right, and then the last one to get a rough sketch. When x equals 2, 3 times 2 is 6 over 2 squared plus 2, 6 minus 2 gives me 4. So that's going to give me a positive value. That is also +3/2. So this section of the graph will also be above. So it's going to approach the vertical asymptote to the left, flatten out, approaching the horizontal asymptote on the right. And you'll notice that we do approach that end behavior over here at 0 to the left and also at 0 on the right-hand side. Okay, that was a chunk of time just for the intro and to get that particular first question done with its graph. So I'm going to take a quick little break, come back with another video so you can see just characteristics of examples 2 through 4.